Good day, I am James Angelo Silipiao, and for this video we are going to talk about families of digital subscriber lines and broadband technologies. The objectives for this video are to enumerate and discuss the families of digital subscriber line or DSL and to discuss the different broadband technologies available today. But before we formally begin, let us first understand what digital subscriber line or DSL is. The digital subscriber line is a family of technologies that provides digital data transmission over the wires of a local telephone network. DSL utilizes the same cabling used for normal telephones, but it can offer higher data rates through the use of digital modem technology. DSL originally stood for Digital Subscriber Loop, and it increases data transmission rates by a factor of 20 or more by sending signals in previously unused high frequencies. DSL technology has added a new twist to the utility of twisted pair telephone lines. The first installation of DSL started in 1998. DSL can carry both data and voice signals, and the data part is continuously connected. Speed in a DSL can go as high as 6.1 Mbps, and the typical speeds are between 128 kbps and 1.54 Mbps. Presented in the screen is a generic DSL reference model. As shown, a DSL consists of a local loop or telephone line with a transceiver at each end of the wires. The transceiver is also known as a modem or modulator or demodulator. The transceiver at the network end of the line is called the line termination or the transmission unit at the central end. The LT may reside within a digital subscriber line access multiplexer or a DLC-RT for lines fed from a remote site. The transceiver at the customer end of the line is known as the network termination (NT) or the transmission unit at the remote end. The majority of DSLs are served via copper lines extending all the way from the central office to the customer's premise as shown in the figure. To address DSL's limited line reach, a repeater may be placed near the midpoint of the copper line to boost the signal on the line. However, the installation of mid-span repeaters has a high material and labor cost. More often, DSL service for customers in areas distant from a CO have DSL service enabled by the placement of a DLC-RT in the neighborhood as shown in the figure in the screen. The DSL signals traverse the relatively short copper wire between the customer and the DLC-RT. The link between the CO and the DLC-RT is usually optical fiber. Alternatively, distant areas may also be served via DSL-AM located at a remote site. Sometimes the DSL-AM may be located within a building having many customers. The figure in the screen shows the network architecture for a voice band modem, private line DSL, and switch DSL services. The voice band modem transmission path extends from one customer modem, a local line, the public switch telephone network, a second local line, and a second customer modem. In contrast, the extent of DSL transmission link is a customer end modem, a local line, and a network modem, with the digital transport through the remainder of the network being outside the scope of the DSL transmission path. The private line service is not switched within the network and thus provides a dedicated connection between two endpoints. The private line architecture may contain a service provision cross-connection within the external office. The switch DSL service permits the customer to connect to many endpoints simultaneously or sequentially. Often, the TUC for the switch DSL service resides within the DSL DSLAM, the switching or routing functions may reside within the DSLAM or in a separate equipment. Now, let's proceed to the families of DSL technologies. The term XDSL applies to most or all types of DSL technology. XDSL family tree includes two main branches. The first is the Symmetrical DSL, which are services that provide identical data rates upstream and downstream, while the second is Asymmetrical DSL, which provides relatively low rates upstream but higher rates downstream. Several types of DSL have resulted from the evolution of technology and the market it serves. The earliest form of DSL is the 144 kbps basic rate ISDN. It was the earliest form of DSL and it was used for ISDN service in 1986, which was then later applied to packet mode ISDN DSL or IDSL, and local transport or multiple voice calls on a pair of wires. Basic rate ISDN borrowed from earlier voice band modem technology. The next type of DSL is the high bit rate or HDSL, which was introduced into service in 1992 for 1.5 Mbps using 2 pairs of wires and 2 Mbps using 2 or 3 pairs of wires. Symmetric transmission on local lines. HDSL greatly reduced the cost and installation time required to provide service by reducing the need for mid-span repeaters and simplifying the line engineering effort. HDSL is widely used for private line services and links to remote networks nodes such as digital loop carrier, remote terminals, and wireless cell sites. In 2000, HDSL2 was introduced to accomplish the same bit rate and line reach as HDSL, but using 1 pair of wires instead of 2 pairs required for HDSL. HDSL2 is spectrally compatible with other services in the same cable within the CSA line lengths, but may not be spectrally compatible if a mid-span repeater is used to serve longer lines. HDSL4 using trellis-coded pulse amplitude modulation for 2 pairs or wires achieves spectral compatibility for 1.5 Mbps transport on longer loops. In addition, HDSL4 further reduces the need for repeaters. The complementary pair of technologies of HDSL2 for CSA lines and HDSL4 for longer lines provide a lower cost and spectrally compatible means to provide symmetric 1.5 Mbps for nearly all lines. Asymmetrical DSL or ADSL service was introduced in 1995 and employed the following new technologies aspect. Higher downstream bit rates are achieved via transmission asymmetry using a wider bandwidth for downstream transmission and a narrower bandwidth for upstream transmission. Near-end crosstalk is reduced by partial or full separation of the upstream and downstream frequency bands. Simultaneous transport of POTS and data is achieved by transmitting data in a frequency band above voice telephony. Use of advanced transmission techniques such as trellis coding, Reed-Solomon codes with interleaving, and DMT modulation were observed in this kind of DSL. Next, rate adaptive transmission that adjusts to the highest bit rate allowed by unique condition for each line. ADSL is widely used for applications benefiting from the bitrate asymmetry. For example, high-speed internet access and workstation access for small business offices and home work office. ADSL supports downstream bit rates up to 8 Mbps and upstream bit rates up to 900 kbps on short lines with moderate line noise. However, to assure service to more lines with more noise, ADSL service is most often provided at bit rates of 2 Mbps or less downstream and 128 kbps or less upstream. The early development of ADSL employed a splitter at both ends of the line to combine the 0 to 3.2 kHz analog voice signal with the ADSL signal in a higher frequency band. The development of the g.lite standard introduced the concept of enabling customer self-installation without a splitter at the customer end of the line. This reduced the labor costs to install the service. Field trials of g.lite demonstrated that an inline filter must be inserted in series with most types of telephone sets to prevent problems for both the voice transmission as well as the digital transmission. Subsequently, it was determined that an inline filter permitted effective operation of the full-rate ADSL, whereas g.lite is restricted to about 1.5 Mbps downstream. As a result, the large majority of current ADSL installations use full-rate ADSL, self-installed by the customer, placing an inline filter by every telephone in their premises. The next type of DSL is the consumer DSL. The consumer DSL is a version of DSL trademarked by Coaxial Corp that is somewhat slower than ADSL, with a 1 Mbps downstream, probably less upstream, and has the advantage that a splitter does not need to be installed at the user's end. However, Rockwell no longer provides information about CSDL at its website and does not appear to be marketing it. The next type of DSL is the Rate Adaptive DSL. Rate Adaptive DSL is an implementation of ADSL that automatically configures the modem at a startup as its rates according to the quality of the phone line. Like g.lite, RADSL supports a much slower maximum data rate, which is 1088 kbps than regular ADSL. It is said that the Rate Adaptive DSL is the most robust business DSL available today. The next type of DSL is the Symmetric DSL, or SDSL, improves on the older HDSL technology by implementing the same basic data rate of 1544 kbps while requiring only a single phone line. SDSL support data rates up to 3088 kbps. The next type is the single pair high bitrate DSL or SHDSL. Single pair high bitrate DSL or SHDSL products were available by the end of 2000. Like the non-standard 2B1Q SDSL system, SHDSL supports symmetric transmission at bitrates from 192 kbps to 2.32 Mbps while providing at least 2000 feet greater line reach than SDSL. Furthermore, the SHDSL specification provided for the use of multiple pairs of wires and mid-span repeaters to achieve greater bit rates and line lengths. SHDSL uses trellis-coded pulse amplitude modulation, which is also used for HDSL2 and HDSL4. The next type of DSL is the Prestandard Very High Bitrate DSL or VDSL. The Prestandard Very High Bitrate DSL or VDSL system were used in field trials in 2000. VDSL supports asymmetric bit rates as high as 52 Mbps downstream or symmetric bit rates as high as 26 Mbps. The key distinction of VDSL is its limitation to very short loops as short as 1000 feet for the highest bit rates or up to about 4000 feet for moderate data rates. The very short line length operation depends on shortening the copper line by placing an optical network unit close to the customer site and then connecting one or more optical network unit to the network with a fiber. Like ADSL, VDSL is a rate-adaptive system that provides for simultaneous transmission of data and an analog voice signal. The next type of DSL is the IDSL. ISDN DSL or IDSL implements a hybrid of DSL and ISDN solution. IDSL offers only limited data rates, which is 128 kbps, although multiple circuits may be bonded. Whereas a unidirectional DSL or UDSL is a proposal from a European company, which is a unidirectional version of HDSL. And another type of DSL is the X2-DSL, which is a modem from 3Com that supports 56 kbps modem communication but is upgradable to new software installation to ADSL when it becomes available in the user's area. 3Com calls it the last modem you will ever need. Shown in the figure in the screen is the evolution of DSL through the years, wherein the dates indicated publications of relevant standards. Presented in the screen is a comparison of DSL technologies in terms of data rates, loop reach, mixed gauge wire, service types, principal applications, modulation, common protocols, standards, and number of wire pairs. Shown in the figure is the upstream and downstream rates supported by the various DSL technologies with the symmetric technologies, ISDN, SHDSL, HDSL, residing along a line of symmetry, and the rates adaptive technologies ADSL, VDSL, covering a broad range of bit rates with the corresponding maximum line lengths indicated in the screen. Now let us proceed with our next objective, which is the broadband technologies. Broadband technologies, communication technology that can employ different channel of data or data streams by using any medium such as air or physical. Different types of broadband technologies are available today, which can be divided into two categories: wired or wireline technologies and wireless technologies. For wired or wireline broadband technologies, we have copper wires. Copper wires are defined as the legacy telephone unshielded copper twisted pair, providing broadband connections by using XDSL technologies such as ADSL or ADSL2+. Newer copper-based technologies such as vectoring and GFAS can deliver higher speed but suffer from the same limitations. They demonstrate bridging technologies towards complete fiber optic cable infrastructures. The next type of wired broadband technology is a DSL or digital subscriber line, which we discussed a while ago. Digital subscriber line is wire transmission that uses traditional copper telephone lines. DSL-based broadband provides transmission speeds ranging from several hundred kbps to millions of bits per second. The availability and speed of your DSL service may depend on the distance. The next type of wired broadband technology is the coaxial cables. The classical cable connections would be the two wires of the telephone line, twisted pair, most prone to disturbance effects such as interference. Broadband internet via coaxial cable is usually offered to customers via the existing cable TV network. The coaxial cable consists of a copper core and a copper shielding coat, and the TV cable networks are therefore much more efficient than the traditional telephone networks. Next is a cable modem. Cable modem service enables cable operators to provide broadband using the same coaxial cables that delivers pictures and sound to your TV sets. Most cable modems are external devices that have two connections. They provide transmission speeds of 1.5 Mbps or more. Subscribers can access their cable modem service by simply turning on their computers without dialing up an ISP, or you can still watch cable TV while using it. Transmission speeds vary depending on the type of cable modem, cable network, and traffic load. And the speeds are comparable to DSL. The next type of wired broadband technology is fiber optic technology, which converts electrical signal carrying data to light and send the light through transparent glass fibers about the diameter of a human hair. Fiber transmits data at speeds far exceeding current DSL or cable modem speeds, typically by tens or even hundreds of Mbps. The actual speed you experience will vary depending on a variety of factors such as how close to your computer the service provider brings the fiber and how the service provider configures the service, including the amount of bandwidth used. The same fiber providing your broadband can also simultaneously deliver voice and video services, including video on demand. Telecommunications providers sometimes offer fiber broadband in limited areas and have announced plans to expand their fiber networks and offer bundle voices, internet access, and video services. Variations of the technology run the fiber all the way to the customer's home or business, to the curb outside, or to a location somewhere between the provider's facility and the customers. T1 or T3 lines are reserved circuits that are usually leased or rented from a company for telecommunications. It operates over copper or fiber cables and used mainly by businesses to connect offices that are geographically separated with voice and data communication. This type of wired broadband technology is expensive and rarely used for residential purposes. Now let's go to the wireless broadband technologies. Wireless broadband connects a home or business to the internet using a radio link between the customer's location and the service provider's facilities. Wireless broadband can be mobile or fixed. Wireless technologies using longer range directional equipment provide broadband service in remote or sparsely populated area where DSL or cable modem service would be costly to provide. Speeds are generally comparable to DSL and cable modem. An external antenna is usually required. The first type of wireless broadband technology is the fixed wireless broadband. This type of wireless broadband allows consumers to access the internet from a fixed point, while stationary and often require a direct line of sight between the wireless transmitter and receiver. These services have been offered using both licensed spectrum and unlicensed devices. For example, thousands of small wireless internet service providers provide such wireless broadband at speeds at around 1 Mbps using unlicensed devices, often in rural areas not serviced by cable or wireline broadband networks. The next type of wireless broadband technology is the wireless local area network, which provide wireless broadband access over a shorter distance and are often used to extend the reach of a last mile wireline or fixed wireless broadband connection within a home, building, or campus environment. The next type is the wireless fidelity or Wi-Fi. It is a fixed short-range technology that is often used in combination with DSL, fixed wireless, fiber, or cable modem service. It uses radio waves similar to two-way radio communications and uses unlicensed devices and can be designed for private access within a home or business or be used for public internet access at hotspots, such as restaurants, coffee shops, hotels, airports, convention centers, and city parks. The next type of wireless broadband technology is mobile wireless broadband or 3G, 4G, and 5G. This wireless broadband is a high-speed wireless broadband connection that is accessible from random locations. Locations depend on the provider's cellular towers and monthly service plans, continually being upgraded to provide data transmission speeds considered to be broadband. These services are generally appropriate for highly mobile customers and require a special PC card with a built-in antenna that plugs into a user's laptop computer. Generally, they provide lower speed in the range of several hundred kbps. The next type of wireless broadband technology is the long-term evolution or LTE. It provides increased peak data rates, reduces latency, scalable bandwidth capacity than 4G predecessors, can manage multicast and podcast streams, and can handle quick-moving mobile phones, and it uses an IP-based network architecture that allows for seamless handovers for voice and data to older model cell towers. Satellite broadband is another form of wireless broadband and is also useful for serving remote or sparsely populated areas. Downstream and upstream speeds for satellite broadband depend on several factors, including the provider and service package purchase, the consumer's line of sight to the orbiting satellite, and the weather. Typically, a consumer can expect to receive or download at a speed of about 500 kbps and send or upload at a speed of about 80 kbps. These speeds may be slower than DSL and cable modem, but they are about 10 times faster than the download speed with dial-up internet access. The next type of wireless broadband technology is the broadband over power line or BPL. In broadband over power line or BPL, broadband can be delivered over existing low and medium voltage electric power distribution networks. BPL speeds are comparable to those of XDSLs and coaxial cables, and it can be provided to homes using existing electrical connections and outlets. BPL is an emerging technology that is available in very limited areas. It has significant potential because power lines are installed virtually everywhere, alleviating the need to build new broadband facilities for every customer. That is the end of our presentation. Thank you for listening.